All right. Well, hello, everyone. Welcome to the 2021 Wolfram Technology Conference. So it has been the tradition for the last 32 of these conferences for me to give an opening keynote and talk a little bit about what we're doing right now, things that have happened during the past year since the previous conference, and a little bit about plans for the future. So let's get going. It's a shame we're not able to do this in person yet again. And I do appreciate all the people who have who've been coming to these conferences for many years. Also pleased to see, I hope, lots of new faces here. Also welcome to people online in the live stream world who may be watching this. So, as I say, pity we're not able to do this in person. Although I have to say the pandemic has been, I think, okay for us. In a sense, our company has been preparing for this for 3 decades. We've been quite geo-distributed. I've been a remote CEO now for 31 years. Now it's only a question of the rest of the world living the way that we have been living. But there are many things that have been coming together for us in these times. I would say in 3 primary areas: technology, deployment, and outreach and communication. And I'll talk about all of these things. But I will say that the things that I'm going to say here are really just a bare outline of the kinds of things that are going on for us with our technology and so on. There'll be many other talks that will go into much more detail from other folks at our company, in addition to all the talks from outside people about the things that they're doing, but there'll be lots of talks from people within Wolfram Research talking about things that we have going on. But I will just try and give sort of an outline here. So, okay, what is the really big picture outline? It's the really big picture outline, as far as I'm concerned, is for the last 35 years since we started our company, the goal has been to kind of realize the promise of the computational paradigm, to understand what's possible to do with this idea of computation, and then go actually build practical tools to be able to do it. And what has happened is the sort of the main thing that has made that possible is the computational language that we built, Wolfram Language, whose goal is to sort of represent everything in the world computationally. And it's worth remembering kind of the divergence of that goal from sort of traditional goals of people building programming languages and so on. The traditional goal has been take computers as they are and provide kind of wrapping around that to make it possible for people to tell the computers what to do at their level, so to speak. The goal of computational language has been, and I've increasingly understood this as the years have gone by, something quite different, which is take the outside world as it is and try to connect, to try to find a way to represent the things that one's interested in the world computationally, so that we humans can specify things in a way that both we understand more clearly in this kind of computational notation, and that we can communicate to our tools. And that's kind of the goal of Wolfram Language. And in a sense, what we've been doing for the last 35 years is building this kind of taller and taller tower of both ideas and technology. It's at this point, I think, a very tall tower that allows us to both reach a lot of things and also see a long way. It's also a tower that is quite isolated in the world, so to speak, in the sense that it's a tower that has reached far into the future, so to speak. I think I was talking last year about the things that we do as kind of artifacts from the future, that we've been able, by building this kind of tower of ideas and technology, to kind of get to things which people might not have thought would be possible for another 50 years or so. That's something which is both exciting from an intellectual point of view. It's also something, and it's also a great opportunity in terms of people using what we're doing. It's also a little frustrating from the point of view of having things that are sort of from 50 years in the future and trying to explain them to the world as it is today. Well, talking of the passage of time, one of the things that we should recognize is that it is almost exactly a third of a century since Mathematica version 1 was launched. It was launched on June 23rd, 1988. next week, depending on how you compute your centuries. We've been discussing that a bit in connection with all of our careful, astronomically oriented time computation capabilities. But it's coming up basically next week on 1/3 of a century since Mathematica version 1 was launched. It's worth reflecting a little bit on what's happened since that time, what's happened in that 1/3 of a century, what's happened both in terms of our technology and what's happened in terms of technology in general. I think that it's worth remembering that I occasionally need to use things that I built in the, let's say, beginning of the 1990s. And I'm always very pleased to see that even the notebooks, even the Wolfram notebooks that were created at that time and the Wolfram language code, it's still, with almost without exception, still runs exactly the same today. And that's a very satisfying realization in terms of building this kind of tower of capabilities, that the things we built back a 1/3 of a century ago are still valid and still work today. You know, just as I was getting ready for this talk, I realized that for some reason, right in the space that I have here, that I realized there was I don't know quite why this is here, but there's a computer that I saw was here, which turns out to be a little bit younger than Mathematica. I think this one is from 1991, but that kind of gives us a sense of the state of computers. That was the kind of the leading edge. It's worth remembering back in 1988, it was sort of the somewhat early days of personal computers. PCs were limited to 640K of memory. The Mac had come out in 1984, was able to run, you know, a couple of megabytes of memory and things like that. But it's the thing that I think is interesting. Well, let's take a look. I think I had some examples here of kind of to give a sense of the time. I thought it might be fun to see here. Let's see. Oh, that was the version 1 startup screen for Mathematica, if you have not seen it. And people, when Mathematica first came out, there were such headlines as this that came with it. But it's interesting to see if you look at, for example, oh, that didn't work very right. Well, if you can see this, is the front page of InfoWorld magazine. I don't know whether that's still around, might be. Bet it's not printed anymore, from June 27th, 1988. And at deadline, before social media, that was the way to get out fast news. Something down here about Mathematica, together with information about the 386 and OS2 and other kinds of computing things of the time. Let's see if we can pull this up here. There we go, maybe, no? Yes, there we go. Don't know why it's over on the side of the screen. So this was a review of Mathematica. It's kind of interesting to see some of the things that were kind of around at the time. There's a current Macintosh of the time, and the beginning of Adobe Illustrator and all kinds of things like this. And then there are some notebooks with their same cell brackets that they have today. The overall UI looks a little different, although it's that's really the surface level of the UI from the Mac OS. Okay. We see other kinds of things here, but as we go down and look at, I think that was a physical software store back in the day, and other kinds of things that were part of the computing world at the time. If we zoomed in and looked at the Wolfram language code here, I don't know if we can do that, probably not. What we would see is something that I consider very sort of satisfying, which is that, well, actually, that code is exactly the same today as it was then. So it kind of feels like we're, in a sense, what I had done in starting to build Wolfram language was my goal was to sort of take this idea of computation and do something a little bit like what one tries to do in natural science and sort of drill down to find the underlying component parts, the underlying primitives from which this idea about computation could be built up. And as some of you may know, Mathematica was kind of came behind a thing called SMP, which I developed in 1979 to 1981, which was kind of my first computational language effort. And Wolfram Language takes the good ideas from SMP and leaves behind the ones that weren't so good. But the overall goal is take this kind of idea of computation and figure out what are the kind of primitives from which that could be built. And what the core of those ideas had to do with this notion of everything is represented as a symbolic expression, and everything we do corresponds to transformations between symbolic expressions. And those ideas have turned out to be extremely powerful and have kind of been the foundation for this tower that we've been building all these decades since. But what's very satisfying is that the core ideas and the design of the language, which were intended to sort of be as foundational as possible, that's worked out. Those things are very pure, very abstract, very foundational, and they survive. And somehow it reminds me, when you see sort of archaeological artifacts from ancient Egypt or something, and you see, an icosahedral dice, you say, well, that's a very modern looking thing. Well, actually, it's 4,000 years old or something, but it's just an icosahedron. And an icosahedron is this sort of perfect abstract form, and it looks as modern today as it did back then. And so I like to think that what we've been able to achieve with the kind of core design of Wolfram Language is something that has that same kind of longevity and looks as modern today as it did a third of a century ago. And it's something that, like mathematics and like other kinds of abstract pursuits, is something that sort of has this continuing freshness to it. I think that in fact, in a sense, I have gradually understood how strong these kind of principles that we started from actually are, and how successfully we can build this tower. Now, I have to give one footnote that I'll talk a little bit more about later, which is that I've realized in this past year that we were actually extremely lucky, that if I had understood more about the kind of theory of evaluation of expressions and so on, I might have freaked out and decided that Wolfram Language was impossible. And that the way that we do evaluation is something which is, as a practical matter, works extremely well. But as a theoretical matter, there are all kinds of interesting issues, which I think we're about to now start exploring through the banner of what I'm calling multi-computation. And I'll talk a little bit more about that later. But I've realized in this last year, I kind of had this strange discovery that, and this is something which has come out of our physics project, actually, this understanding of the sort of foundations of computation, that we were actually very lucky. We kind of managed to navigate through something which could have been just unimaginably complicated and prevented the possibility of a practical system of the kind that we've been so successful building. Now, I will have to say that well, let's see, it's perhaps interesting to understand, to sort of, again, contextualize that third of a century, to realize that that's about exactly half the time that computers have been sort of real things in the world. 1955 was the time when the first mass-produced computer, the IBM 650, came out. And I think I might have a picture of what that consisted of. Let me see here. Do we have this? Oh, come on. Humph. Oh no, this thing is too clever for its own good. I think it's oh no, come on. Oh well. All right, I was going to show you a nice simple slide of something, but oh, there we go. Okay, I think what happened is this was a PDF document, and I think we just imported the whole book into Wolfram Language as a piece of computable data, which was kind of not the idea. But anyway, this was that's an example of what an early book about programming the IBM 650. And I suppose one thing I find interesting looking through this book with all its flow charts and so on is that a lot of what people still think of as programming is that same kind of activity that was being done back in 1955 with the very first computers. First you do this, then you do this, then you do this. And it's interesting to realize what's changed and what has not. And in fact, in a sense, this kind of idea that instead of trying to write a programming language that goes from kind of the machine up, this idea that we have in computational language of going from the world down, so to speak, is a different idea, and an idea that is still slowly getting absorbed as the decades go by. And I think the thing that I see, I think is much more analogous to what we're doing. Rather than being a thing that operates a machine, what we're doing is providing, in a sense, a notation for thinking about the world. And just as maybe 400 years ago or so now, mathematics went through this transition from mathematics being described by words to mathematics being described by a notation with plus signs and equal signs and so on. And that idea of being able to streamline the presentation of mathematics through that kind of notation, that's what launched algebra and calculus and basically launched the mathematical sciences. And the way I see it today, the great opportunity that we have with computational language is to provide that computational notation for thinking about things, both for ourselves as humans thinking about things computationally, and with the assistance of computers being able to go further and to use this kind of computational language as the notation to drive the creation of essentially the computational sciences, or even beyond the sciences, kind of the general computational X. That's the opportunity in this time, just as 400 years ago, there started to be a great opportunity from the invention of mathematical notation. We've now spent the last 40 years basically building this computational notation that is now Wolfram language. Well, it's actually notably I would say that one of the things that's happened over time, we've been both the technology we've developed has developed a long way, but also back in the day we used to sell floppy disks through neighborhood computer stores, and gradually the process of distributing software and all the different ways that one can deliver this technology have evolved. And I'll talk a bunch about deployment in a little bit here. But I would say one thing that I'm also quite proud of from a purely business point of view is that the mechanism by which we have run our business has been very kind of straightforward and consistent and transparent from the very beginning, in the sense that we just sell software and the people who use the software pay for it. Over the course of that period of time, we've seen many other business models like give the software away. You know, we see as every year, I think in this year, I've been slowly trying to informally count the different bait and switch strategies used by people who say, we've got this great open source thing. Well, yes, but, et cetera, et cetera, et cetera. I think that business model is showing its it's many have come and gone over the last 35 years, and I think the model that we have, I'm kind of proud of the fact that we've been able to keep as consistent as we have, and we intend to do that going into the future. So both consistency in terms of the compatibility of our software and consistency in terms of the way that we deliver that software, while also paying attention to all the different possibilities that exist as time goes forward. Well, so if we kind of look to get a sense of what's happened, let's see. This is kind of a chart of kind of the areas in, if you look at the root guide page, the front of documentation for Wolfram language today, you'll see a bunch of different category areas. This is a plot as a function of time of when those category areas kind of came into existence. At the beginning, there was sort of core language and the mathematical application area. And then in the mid-2000s, there was this kind of sort of Cambrian explosion that occurred. If we kind of compress the scale a bit, we'll see there's the Cambrian explosion happening in the mid-2000s, leading to all these different application areas here. Well, it's interesting that how this has sort of evolved over time, and this has presented us with a couple of things. It presented us with something of a challenge. At the beginning, a third of a century ago, we have this great product whose name was Mathematica, and over time, the thing that this math blue line here has fragmented or has grown this kind of explosion of other different phyla and so on of capabilities, to the point where in the around just after about a decade ago, we decided we should call what we have now Wolfram Language, rather than talking about Mathematica as that particular application area. Now, a couple of things have happened in the past 35 years. One of the things that's happened is, what is math? You know, it's interesting that that book I was showing you about the IBM 650 was written, who was going to write a book about computing back in 1955? Well, it was a math professor. But over time, math didn't go in the direction of saying, this idea of this formal approach to the world is going to cover the computational kind of direction. Math went in a much more specific direction, and I think I had a better understanding of that through my work in new kind of science. And actually, I'll talk a bit more about the kind of paradigmatic aspects of mathematics versus computation versus multi-computation and so on later. But the thing that has happened is that the mathematical paradigm is an important thing, but it is separate from this computational paradigm, which is the kind of the new paradigm of the 21st century and so on. And so that's presented something of a challenge in terms of explaining what it is that we have. Because when we say we have Mathematica, people say, oh, that's a thing about math. And when we brought out Wolfram Alpha, we consciously decided that we should just throw the meaningless name, the Wolfram name, which is a kind of in a sense, a meaningless word to describe what we have, rather than trying to describe it in terms of something which is a sort of descriptive word of which there isn't one, for a computational knowledge engine that has computational intelligence and so on and so on and so on. That's a thing that is sort of defined by what it is. So one of the things that we've been grappling with for the last several years is, what is the relationship between Wolfram Language, Mathematica, and the deployment and delivery mechanisms that we have, in particular now Wolfram 1, which is our sort of general product that delivers the desktop and cloud and so on experience with Wolfram Language. And so what we've decided to do, we've been circulating around. If there's Mathematica, there's Wolfram 1, they're both based on Wolfram Language. How do we deal with this? As of now, Wolfram 1 and Mathematica are about to be basically identical products. And what we intend to do going into the future is this is now sort of our restarting point. And in the future, Mathematica will evolve in whatever direction makes the most sense to support essentially the mathematical paradigm, and Wolfram 1 will evolve in whatever direction makes sense to support the computational paradigm. And these are things which, as I say, as of today, they're starting from exactly the same place, but you can expect to see progressive divergence. And right now, it doesn't really matter which one you're on right now, but if you're going in the direction of general computational applications, Wolfram 1 is kind of the direction to go. If you're going more in the mathematical sciences, then Mathematica is the one to go. So that's kind of what we're planning to do as far as that's concerned, and both are based on Wolfram Language. Okay, so what do people do with all of this? Well, I wanted to show you one thing. I'm afraid this technology is not working quite as I would like, but oh yeah, I should show you this also. This is a plot reflecting that kind of Cambrian explosion picture that I showed. That's the number of built-in functions in our system as a function of time. And this is kind of the inflection point here, where we start to see this continued rapid growth as we're able to understand how to build and actually build in this kind of computational direction to really build out our sort of full-scale computational language. Okay, let me show you this. So one question is, what do people do with all of this? Well, it turns out they write about a paper an hour that makes use of Wolfram Language, Mathematica, whatever. This is a quick video made, of course, with our technology of papers that we know used Wolfram Language that came out during the past year. So see if you see your paper flash by here. But in any case, I would like to say that if you are writing such papers, please do actually refer to us. It helps everybody, and we've tried to make it easier to do that by the fact that at the bottom of every function page, you'll find, if I go to the bottom here, you will find cite this as, and it gives you in all the different citation formats, it gives you a click to copy thing that you can put right into your paper to cite this particular function. And I think that's you can cite the whole Wolfram language system, but you can also cite individual functions that you're using, and that's kind of the anchoring for how a particular piece of work might have been done. And I also would like to say that I would like to ask people, just as it's great to cite what we've done if you found it useful, please don't remember that you can add things that are relevant to Wikipedia and other websites and so on. We typically cannot add things to these websites. So nothing about what we do will be added there unless outside people do it. And so that's something we'd like to encourage people who are interested to do that. Well, so let's talk about some of the specific things that have been going on. Just right after last year's technology conference, version 12.2 of Wolfram Language came out. There's a kind of word cloud illustrating what was in it. Just in April of this year, version 12.3 came out. I'll be talking to you today about the approaching release of version 13 of Wolfram Language. I consider it extremely impressive that in the past year, we've had 2 surprisingly major releases of our system. I think I could show you just as a very, very quick outline of sort of what came in version 12.2. This is stuff I had a chance to talk about a bit last year. We introduced biomolecular sequences. We introduced spatial statistics. We introduced a kind of PDE modeling language. We introduced the ability to have tech input directly in notebooks. We introduced the canvas capability for drawing things. We introduced the molecular drawing tools. We introduced a bunch of new math capabilities. We introduced, including ones for asking about functions. We had the first iteration of video. We had first ability to do batch submission to cloud providers. We had a variety of new multidimensional plotting capabilities. We had 3D array plots. We had all sorts of new plot theme ideas. We had ways to type code more beautifully. We had a variety of new array operations, more kinds of echoing, the confirming close framework for symbolic exception handling. And we had a variety of functions like with cleanup and so on, new dates and calendars, some new capabilities in Geo Computation. And we also had the first iteration of importing PDF, convex optimization. Wow, my thumb is not even at the bottom yet. Synthetic geometry, additional capabilities there. And let's see, more and more here, more in machine learning, just lots of different kinds of things. This was just in version 12.2. Now, in general, what we're trying to do with these versions of our system is the incremental versions are basically whatever we have ready, roughly every 6 months or so, that's our plan, we will deliver in a point X release. That means we will have capabilities that are absolutely usable at the time we deliver them, but don't necessarily represent a full story of some particular domain of application. And the integer releases are the places where we hope to have a kind of a full story of what can be done. Well, just a quick outline of 12.3, which came out in April of this year. various convenience functions like solve values and so on. The new theming of dataset for new display of dataset. Well, various kinds of speed increases, courtesy of some early compilation capabilities, more on math and transcendental functions, a lot of things in symbolic optimization, graph theory, more synthetic geometry. Again, you can see that there are certain themes that are going on here. This was the beginning of generalizing the notion of axes for plots, so you can have weird shaped axes and so on. This is material characteristics, so that you can have golden toruses and golden knots and so on. The beginning of implementing trees as a fundamental data structure that one can manipulate like graphs. The issues things with dates and times, machine learning, various kinds of explainability of machine learning, new video capabilities, new things about chemistry, things that to do with control systems. It's a long-running story of developing control systems capabilities for Wolfram Language, and the ability to download them to microcontrollers like Arduinos and so on. Being able to this is some capability I'll show you in a minute. Beginnings of code assistance, various other features of the compiler, things like shell and Java being able to be included in notebooks, to be executed from notebooks, blockchain capabilities, features of remote kernel computation, and so on. All right. So I will be showing you a little bit in a bit. I'll show you some of what we have coming up, hopefully in the next month or so, in version 13.0, that collects together these 12.x capabilities together with a whole bunch of new things added between 12.3 and 13.0, and I'll show you a bunch of those new capabilities in a bit. But first of all, I wanted to talk some more about the general question of deployment. And so the issue is, we've got Wolfram Language, and the question is, how do you use Wolfram Language? How do you actually apply Wolfram Language in a particular place? Well, one of the sort of original story there was, well, you have a desktop application that uses notebooks, and oh dear, this is well, okay, that's me. All right, let's see if it knows me. There we go, that's good. But for the last more than a decade, we've been developing the cloud, and the cloud allows us to have, just in a web browser, the same kind of notebook capabilities that we have on the desktop. For those who really follow these things in great detail, the new documentation is better tagged for what exactly is impossible in the cloud or impossible on the desktop, so that you can get a sense of that. But the thing that so sort of the first story of the cloud is the ability to have notebooks that can migrate between the desktop and the cloud. You can take this this cloud notebook and peel it off to make a desktop notebook. That's just open this file in Wolfram Desktop. There we go. I don't need that. Oops, it's downloading. Oh, no, I do not want that. I pressed the wrong button there. But anyway, I can peel this off and download that file to use as a desktop file. Or I could say I could take some desktop file here, and I could have some something that I have created on the desktop, and I can, with great fidelity now, be able to just take this file and say, and this is something that we have been progressively, and be able to just say, publish this to the cloud. And so that will now, let's just say, automatically assign a URL to that, publish this to the cloud. Now that will create a cloud version of that I can go and There's the QR code if you're giving a lecture in person, I suppose, in the future, because now you could just go and put it in Zoom chat or something. But in the future, when you're doing it in person again, people can hold up their phones and get to that QR code. And now I can go view that notebook here. Now, the workflow is, this is a published notebook. It should load as fast as HTML loads, but it will have all of the capabilities of an actual Wolfram notebook, and it will have manipulate and so on. And we're now making it to be something where up to a reasonable point, you can publish any notebook and be able to have interactive things for that people can access in that notebook. But then if you want people to be able to edit it, you can say, make your own copy, and then it will, you will be able to sign in, for example, to Cloud Basic to get, which is a free version of the cloud where you can have at least temporarily stored files, but then you can go in and have a version of this that you can now edit and do computations with. And so this is, that's one piece of the sort of the workflow that we've been developing for the past decade or so, is this kind of smooth flow between the desktop and the cloud. An important thing that just came one important feature of all of this is single sign-on. Is particularly relevant for universities and other large organizations where it's possible to use the central authentication mechanism to be able to sign in to the cloud, and also will be possible to sign into desktop and just using that single sign-on capability. And we've been seeing over the past month or two just a tremendous rollout among universities, particularly of single sign-on capabilities, which just makes it a lot easier for people to access what we have. Now, I want to say that another thing when it comes to these, to what's in the cloud, the embeddability of this in other sites has been greatly enhanced. We now have this notebook embedder. The notebook embedder is, for example, used in the Wolfram community, and the notebook embedder is a way to take something like this and just embed it in a website and give you capabilities to sort of pop it out into a full notebook and so on. Well, I should say there's another piece to this whole thing, which is the cloud rendering API. So let's say that you just have somewhere on the web, you have a bag of bits that is a notebook. How do you get that rendered? Well, the answer is there's now an API, wolframclouds.com/view, which will just take any bag of bits from somewhere in the and render it as a notebook. So this, I guess, is a piece of something that I had written about the physics project, but now this is, I guess, that's a bitmap. Oh no, it isn't a bitmap. There it is. So you can do all the kind of notebook things, but the point is that this is just something where you can point this this viewing API, cloud rendering API, at any bag of bits that represents a notebook, and have that be something that comes up as a notebook that you can then have, you can do sort of basic interactions with, and you can then peel off if you want to actually edit and so on. So another great mechanism for taking, our goal is to make it so that notebooks are the generic source that you can use for documents that now become computable documents, and that can be deployed in a way that can be as sort of effective on the web as raw HTML, but just an awful lot easier to author, and with much richer capabilities. That's our goal there. And I think it also helps when you're doing kind of mathy things that we, for example, have this immediate tech input that works both on the desktop and the cloud. So you can really generate documents that are really rich documents directly as Wolfram notebooks. Well, when it comes to supporting notebooks, there is the desktop, there is the Wolfram Cloud, and there also is our enterprise private cloud, which is a private version of our full cloud infrastructure. And this has been something which in the past year, we've seen a nice pickup of these capabilities by lots of organizations installing enterprise private clouds, which allow one to locally serve cloud notebooks and to have cloud computing capabilities locally provided through our technology in the cloud. So the whole question of sort of what are the different possible ways to deploy Wolfram language? Well, it turns out there's a stack of them. And Wolfram Cloud, the public cloud is one, the enterprise private cloud is another. These provide kind of notebook capabilities. There's a new thing that just came out in April of this year, which is Wolfram Application Server. Wolfram Application Server is a very industrial strength, but in a sense, lower level way to deliver Wolfram language capabilities. It delivers not notebooks, not the full interactive notebook experience. It delivers APIs, which you can also get from our public cloud and the enterprise private cloud. But Wolfram Application Server is a sleek API delivering system, and it runs. It's a very scalable thing running inside containers with clustering and all kinds of things like that. And that's something that just came out in this last year. There's also WSTP server, which is a local server that can run on a particular computer that allows one to connect Wolfram script, the sort of the command line version of things to this persistent WSTP server. And I think, there we go, here's another new thing. This is a Wolfram language runtime for AWS Lambda. This is running in the Amazon Web Services environment, the ability to just call a Wolfram language function in that environment. And we're discussing the possibility of having this work in other cloud environments as well. So those are different. So if you're running in AWS and all you have is just, I'm running this function, this AWS Lambda mechanism is the right thing. If you want to have something which is a more sort of a fully clusterized industrial strength way to deliver APIs, the application server is the right thing. Application server doesn't deal with, for example, having separate users. It's just you ask for an API, you get back the results from the API. If you want to serve notebooks, if you want to have all sorts of things with users and so on, then the enterprise private cloud is the solution for that. Well, okay, so there's also underneath, I should have explained, there's application server. And there's application server in Kubernetes. There's its lower level representation, so to speak. This is AWS Lambda. That's its kind of low level presentation. Well, okay, so underneath all of these things is our Wolfram engine. And there is a free version of Wolfram engine for developers that you can get on all these different platforms. One of the things that we've been doing over this past year is to make it super, super easy to get this Wolfram engine for developers. So making sure that it exists in all sorts of package managers. You know, you can get it. There's the Docker version of Wolfram engine. There's versions in Homebrew and Winget and all sorts of others. So it becomes very easy to just get a Wolfram engine to use somewhere. The other piece of this is supporting more and more IDEs. So you can, if you are writing large-scale programs in Wolfram language, you can do it in a whole variety of environments. And one of the things that has come this year is the ability to have all sorts of syntax coloring and auto-completion working in these other environments like Sublime or like Visual Studio and so on. That is enabled by a new thing, which is our LSP, Language Server Protocol server for Wolfram language. This is something that can be plugged into these IDEs to give them the capability of understanding Wolfram language code at the level that IDEs understand code. So I should mention that the use of our language through other environments we had last year, but this has been further enhanced, the client library for Python, where you can basically just access Wolfram language in a very clean way from kind of the framework of Python, or you can also do it for Java and other languages. So it's been a general thing is sort of, where do Wolfram engines show up, and where does our Wolfram language system get used? And there are an increasing number of different applications out there in the world which have Wolfram engines inside, and I know a bunch of organizations that provide such things are represented here at our conference. There are things in intelligent assistants, there are things in desktop systems, in cloud systems, in standalone devices, and so on, all with kind of Wolfram engine inside. I would say that one thing that we are working on, and you'll see a bunch of things related to this, is standalone application deployment with Wolfram engines, being able to have both command line and UI-based applications that just launch from the operating system and have a Wolfram engine inside. And part of the way that's being achieved is to have kind of a way of wrapping Wolfram engines into applications with a minimum footprint Wolfram engine for that application being included in the application. Well, so among places where there's sort of a Wolfram engine inside, there's a lot that we're doing, even our own company, that makes use of that. For example, every company has an ERP, enterprise resource planning, I guess that stands for system, a transaction processing system. We decided about 5 years ago now that we didn't like the system that we had, and so we decided we would simply build our own using Wolfram language. That's a process that is almost complete and is a quite wonderful example of the power of symbolic programming and the capabilities of a computational language to inform something as sort of core commercial computational as an ERP system. And that's something that we will be initially using ourselves, and maybe we'll spin it off as something to be available to other people as well. It's an interesting example of use of Wolfram language. I might say that another thing that has been continuing to happen is being able to provide not just the raw technology that we have, but finished services around that technology. And our two large groups, Wolfram Solutions, that provides large-scale solutions for technology, and Technical Services Group that provide more direct, implement this particular thing solutions for technology around using Wolfram language. Both of these have been doing all sorts of interesting projects in all sorts of different domains, which I think will have been things that are getting deployed in interesting ways in the world. Well, so we have all sorts of things going on with partners and other organizations. One that I just wanted to mention, because I think it's a particularly interesting one, is one that's going on with Microsoft. This relates to Excel. If you get a modern version of Excel, you will find the beginnings of an integration with Wolfram language in Excel. So this is any old Excel here. There is a data tab, and if you pull down the data tab, you will find a variety of data types that are supported, and these are backed by Wolfram language capabilities. So if I'm not a good Excel user, so I apologize in advance for me messing this up completely, but let's see. I will try and type in some things here. Let me type in some names of elements. Okay, let me select the names of these elements. Oh, look at that. It figured out, I think, already that those are, let's see, I press the automatic button. It should go through a natural language understanding system, and it should, if all goes according to plan. Oh, that's odd. Okay, it didn't figure it out. It should have figured it out. Okay, I say that's a chemical element. Right, let's select that as a chemical element. Let's select this as a chemical element. Select that as a chemical element. Okay, that one, select that as a chemical element there. Now we've got a bunch of chemical elements, and now in Excel we can see here, let's ask for the crustal abundance of those elements. We should be able to go, no, I didn't know how to use Excel. I knew that was going to happen. All right, let's see, let's try, how about let's do known isotopes. So let's see. Okay, there we go. So that's now just injected into Excel from Wolfram language is the known isotopes of those various chemical elements. And you'll see a whole variety of different kinds of lots of different capabilities here. Let's take a look at what some of those are. This is just a general page about this, but I think we have, yeah, if we go here, let's say food, for example. You can get nutrition labels. You can just type in. You can have an Excel file or type into Excel what you're eating and go and compute nutrition things. You can also actually compute in Excel things about various nutrition goals and so on. And you'll find many of our entity types are available here. So, for example, let's try castles. Okay, so here we've got these are some sample entities of castles, and you can do computations here with, in this particular case, castles directly in Excel. And hopefully there will be more coming. I think there's also integration into other Office products that is planned, and also the ability to just directly call Wolfram Language to compute things directly in Excel is something that's coming. But this should be the case that any Excel that you get now will have that data tab that has access to our Wolfram Language capabilities there. So, okay, more in terms of how we're deploying things. Another example of deployment is from within our core system, is making use of, so within Wolfram Language, the Wolfram Language has the feature that you have to know the language, just as in Mathematica, you have to know something about Mathematica to be able to use it. One thing that we started a couple of years ago now is this thing we call Wolfram Alpha Notebook Edition. And if I can get some, let's see, where do I have that? There we go. So we've been steadily advancing Wolfram Alpha Notebook Edition. And this is, let me just make this bigger. And so in Wolfram Alpha Notebook Edition, you can just type things like, what is the integral of x cosine x or something, and it will then convert it to Wolfram Language internally and then give you the result. And you can then go on and say, you know, something like plot that, and it will give you a plot and so on, all the time showing you what the actual computational language code that was involved in doing that was. But so this is kind of the ease of Wolfram Alpha, but the ability to build things up in notebooks in the way that people have been used to with Mathematica and Wolfram 1 and so on. What we had, so what's happened with this, at first it's been quite popular in the K through 12 sector, also with hobbyists, but we're also finding it used quite a lot in first math courses, for example, at universities. Now, I might say, so there are a few new things in Wolfram Alpha Notebook Edition. There is the ability to enter math in this kind of templated way like this. There's also the ability to have access directly to our demonstrations project so that you can get a demonstration directly in your notebook here from the 12,000 demonstrations that we have in all these different areas. And that's another convenient thing that you can then put that in this notebook and keep going. You can also have, there's a variety of quizzes that are now exist in this environment. So you can do those here. We've also there are a new thing this year is the notebooks that provide starting points for the typical ways that people use Wolfram Alpha Notebook Edition. You know, what's interesting about Wolfram Alpha is there's no documentation for Wolfram Alpha. Basically, people just walk up to it and it's a do what I mean, you know, do whatever I say type system that people just interact with in their natural language. For Wolfram Alpha Notebook Edition, one's starting to be able to do more structured, more built up kinds of things. And so these starting points provide the kind of the scaffolding for people to be able to do that. Okay, so and it's sort of a, the concept here is you can do a complete homework in Wolfram Alpha Notebook Edition, whereas in Wolfram Alpha, it's just a single result that you're getting. By the way, if you're using Wolfram 1 or Mathematica, you can get to the, let me quit that. You can get to, by just going File, New, Wolfram Alpha Mode Notebook, you can get a Wolfram Alpha Notebook Edition like notebook here. And you can, that's a convenient thing. If you're like making homework, you can write it in Wolfram 1 and then just, and students can use it in Wolfram Alpha Notebook Edition. Okay, so other things I might just mention in Wolfram Alpha, there's a lot of new stuff here. There's one of the things that's new is the ability to do kind of math input in mathematical notation in Wolfram Alpha on the web and so on, a variety of other things. I'm not going to talk about this in too much detail here. Okay, so other things that we have been doing, I should say that I had shown those quiz things that we've had for a while, the Wolfram Alpha problem generator, and we've had the challenges website. These are all things that are I was going to show, I was going to show what, yes, this is a calculus homework created to be used with Wolfram Alpha Notebook Edition. So this is a notebook that can be opened in Wolfram Alpha Notebook Edition, can be authored or opened in Wolfram Desktop, or with and can also be run in the cloud. And it's just a piece of workflow to let people who don't know Wolfram language yet be able to do things effectively. Okay, well, continuing. So in addition to the actual Wolfram language capabilities that we have, there's also a variety. One of the general things that we've been adding are these repositories. So we added a number of years ago our data repository, which continues to expand. The #1 download for that in the past year has been, needless to say, COVID-19 data and resources that we've been providing on an ongoing basis to people, and it's led to a variety of interesting studies. We also have, as part of our repository collection, we also have the neural net repository, which gets new neural nets added every week or two of sort of the latest research, and we get to make use of these things in the functions that we create in Wolfram language. So, for example, I think this is a very recently added neural net for finding key points in images and so on. So there are a whole variety of repositories that are coming. We have, we have things like the formula repository. We're going to have the color palettes repository, all sorts of other repositories. Eventually, there'll probably be, we have planned also a repository of repositories. But one of the particularly fast-growing repositories is our function repository. This is, there have been about 620 functions added to this since our last technology conference. And this is it's a very convenient way to add a piece of capability that you want to use repeatedly and that you might provide to other people. You can, given that you, if you go and you just say, you just ask to let's see, where did I go with this? If you just sorry, excuse me. That's very odd. I thought I was okay. So you can, as many of you will know, you can just say File, New, Repository Item, Function Repository Item, and you can just start defining your function here. And when you have it defined, you can either say deploy it locally on your computer, deploy it into the cloud, potentially publish it in the cloud, so anybody who has access you can publish it publicly in the cloud. So given the object ID for the thing in the cloud, anybody can run that function, or you can submit it to the repository where we make a curated collection of these kinds of functions. But what's nice about this, let's pick a random function from somewhere here. Let's say, I don't know, a block cellular automaton here. Okay, so you just click to copy this, you put it in any notebook, and now you can simply run this, because this resource function of block cellular automaton just downloads the code for that particular function from the function repository and then runs it, should run it. Let's see, oh, there we go. And then runs it in your local session. And now that code has been downloaded, and so it will run fast every subsequent time. So there are many ways that we're using these kinds of function repository items. That it's kind of a good way to sort of add functionality ahead of when it's ready for the full language. But let me show you an example here, actually in Wolfram Alpha Notebook Edition, of the use of that. So let's make this a little bigger. So let's say we say, Riemann sum, I don't know, x squared or something. Now this will actually use a function from the function repository, and I could get what just happened here? That should have, oh, there we go. Oh, I was not, okay, right. So now it's going to use that function from the function repository to provide this kind of rather specialized thing. But if I wanted to, I could go ahead and get this, and I could use it in Wolfram Language, and it would all just work because it's accessing things from the central function repository. Okay, so that's the function repository. It's a curated collection of individual functions that do all sorts of specific things. By the way, those functions they're Wolfram language functions, but they can call external code if they want to. And there's now the capability, at least on the desktop, to call things like Python code directly. That's a non-trivial piece of software engineering because of all kinds of horrible dependencies and things like that you have to worry about, of library dependencies and so on, that you don't have to worry about in Wolfram language, but you do have to worry about in low-level programming languages. So the let's see. So that's kind of the story of the function repository. A big thing that is newly coming out is the Paclet repository. So people may be aware of these things called Paclets. Some people have been using them for quite a few years. They've existed in our system. We've used them internally for a long time. A Paclet is a bundle of functionality that deploys itself into a Wolfram language instance. So that bundle of functionality can contain functions. It can contain things that deploy palettes. There's a lot of different exposure points that a Paclet can have in a Wolfram language instance. And so, for example, here, I think, let's see, do I get a new Paclet? Is this available now? Maybe not yet, quite yet available. But there is about to be, oh no, I know how to get to this. Yeah, right. This is the beginning of the new Paclet repository. And the Paclet repository, so here if I say submit a new Paclet, I will get a thing to submit a Paclet. And this is, oh gosh, I have to go through, this is a whole IDE story. I have to actually go through and name a Paclet directory. So I have to go here and say I'm going to create a Paclet that has a certain name. Wake up, put a name, oh, there we go. Choose Paclet directory, okay, my test. Oh, maybe I have to browse for, am I able to do that? Yeah, okay, there we go. So this is now creating a Paclet directory, and now I can start going and adding individual files, putting web content in here, defining the whole story of how my Paclet is going to be presented. And I can package in lots of different kinds of things here, as I say, including not only functions and external libraries and all sorts of other things. But in the end, what will happen is that Paclet will, you can either deploy it yourself and make it available in the cloud, or you can put it in our Paclet repository. And this, unlike the function repository, which is a curated supply of individual functions, the Paclet repository is not going to be curated. It will be kind of a free-for-all. You can put whatever you want here. So you define it with that Paclet definition notebook, and then it deploys, and then it exists on the web here, and then you can go down and you can have examples here. So let's try taking that example. Let's see what that example actually does if we put it into a notebook here. So let's take that example. Okay, so this blob here, let's take a look at what that blob actually is. That blob is going to be a Paclet symbol that is, oh, come now. Okay, somebody made a mistake here, but that's all right. That symbol is this is a way of getting that particular thing. There's a function called Paclet symbol, which is the analog of resource function. That is a thing which will reach in. It will kind of deep grab an individual function from a Paclet to allow you to use that individual function here. You can also go ahead and install the whole Paclet explicitly and load in the functions from the Paclet and do whatever you want with them. But this is a way of kind of grabbing an individual function from a Paclet in a nice transparent fashion. Now, of course, all the issues about whether the Paclet changes from under you and so on, those are all kind of complicated, but this is a capability for doing that. One thing I might say is well, okay, so anyway, that's coming. Now, we've also, in support of the creation of large-scale Paclets, we also have been doing a bunch of work on providing tools for creating things like documentation. And so this is a new palette that is, I wonder if I can make this bigger. Yes, I can. This is a palette for creating documentation of the kind that we have in, you see, this is the problem. When you have a structured system, it insists that you're structured here. Yeah, I should add metadata to this. But in any case, this allows you to easily create documentation that is like the documentation we have for built-in functions. This is has a nice, I hope, ergonomic palette for doing that. That can then, and you can then take this and build it into a Paclet that can be deployed with documentation on the web and so on. So I might mention that in general, so that's about Paclets that people can create for themselves and use themselves. And some of these things like Paclets can install themselves as things that are being mentioned from your instance of the documentation for the system. And for example, you can also, one of the new things, I think it will be here, let's see if it is. Yeah, you can create your own guide page. This is a convenient thing for, if you've got functions you commonly use, you can create your own guide page instead of one of our built-in guide pages. You can create your own guide page. You can then deploy this to the cloud, perhaps publicly so other people can use it, or perhaps privately. And then you can set this up so that it will appear in your version of Wolfram desktop documentation, for example, when you use it, so that you can conveniently find that documentation that you've created. Okay, so in general, with our documentation, there are a whole variety of new categories of documentation that we've been developing. We've had for a while the idea of workflow documentation. That's documentation down here for workflows. That's documentation that is something that requires sort of more than just entering a function in a notebook, for example. It requires something that typically has external interaction And that's something conveniently represented in a workflow piece of documentation rather than our traditional function-based documentation. There's more coming. Feature set pages are one coming attraction of trying to collect together beyond a guide page. A guide page is really a function-centered piece of documentation. A feature set page is something that contextualizes a set of features in some area. And there are a variety of other kind of how to do X type pages that we expect there'll be many of in the future. Something, sort of practical software engineering thing, documentation that we have a lot of documentation and it's very big. And so one of the things that is happening now is that you will be able to have documentation-less downloads. So when you get a Wolfram 1 or a Wolfram desktop or a Mathematica, you'll be able to say, I want it without local documentation. So you're using the web documentation rather than local documentation, but it's a much smaller footprint. I might have mentioned the custom guide pages. I was just showing there. Oh yeah, there are all sorts of new categories of documentation. Our documentation is getting both broader and deeper. So these are method documentation pages. That's a new thing, or documentation pages for batch computation providers. All sorts of things like that. This is an example of a custom guide page created for functions around our physics project. So that's another kind of thing. There also, I was showing you Excel entity pages. That's just another type of new documentation page. So yeah, here's an example of one of those. So this whole problem of explaining all the things that we have, and we have a lot now, there's lots of pieces to that challenge. One thing that we've been developing a lot is Wolfram U. It's been expanding in terms of number of courses and in terms of things like ability to provide certifications. A rapidly growing number of people are getting Wolfram U certifications. Also, we've started different kinds of educational elements like study groups and boot camps. We have a variety of classes that are now online, a data science class, an introduction to differential equations. We have coming very soon signal processing, elementary introduction to algebra, introduction to cryptography. We've had a very large number of training events. There are many new courses in the works. There's one on blockchain that should be coming early next year. Actually, while I'm talking about blockchain, we've been doing lots of stuff with blockchain. Our Wolfram Blockchain Labs has just been working on its 6th blockchain integration. This is with Cardano, and been doing a variety of things along those lines. We've also been doing a variety of things with NFTs. We even did an NFT auction actually of some. I did an NFT selection of cellular automata. They came out really nice, actually. And then the main human part was, in addition to choosing the cellular automaton, was choosing the name. And this was a rather successful auction of these things. And we kind of have understood from that quite a lot more about kind of the role of NFTs as a sort of permanent record of things and so on. And some interesting ideas will come from that. So when it comes to doing things with NFTs within Wolfram Language, you can, oh no, that's not what I wanted to do. Let's see, there we go, let's go in here. So that piece of code should retrieve an NFT from the Cardano blockchain and retrieve the data from the Cardano blockchain to go look up in IPFS an actual image associated with an NFT that was created. And there's the image version of the NFT for somebody's cat. Let's see. At this point in a talk like this, one needs a cat, I suppose. At some level, the blockchain is another deployment channel for another place to lodge a piece of computation in the world. In blockchain, one of the things that is sort of highlighted by blockchain is the idea of computational contracts, contracts that describe things computationally. And really, when you're describing real world things, you need a full-scale computational language. And that's the thing we uniquely have with Wolfram Language. So that's kind of a reason why in the long term, we're likely to be deeply involved with the world of blockchain and things like it. But in the shorter term, one of the things that's needed even for very basic smart contracts and blockchain is an oracle that sort of tells you facts about the world. And we have been kind of really the only serious sort of oracle for these kinds of things provided through the Wolfram Alpha API. We're now developing a sort of full-scale oracle system for a variety of different blockchains to provide oracles for smart contracts directly within the blockchain. Well, so let's see. We're always doing all sorts of different kinds of things, from NFTs to all sorts of core development, to all sorts of basic science. And I would say that we have sort of a portfolio of activities that span from the this year to this century kind of timescale. So since last year, a few of the things that were kind of in the longer timescale type of domain, let's see, where is this? Yeah. Last December was the 100th anniversary of these things called Combinators, which was sort of the first, actually the very first formal example of universal computation, even before Turing machines, 16 years before Turing machines. They are represented very beautifully and simply in Wolfram Language, and they are very abstract kinds of things. And they are sort of an example of symbolic computation, a very early example of symbolic computation. And they were in some ways an inspiration for the way that I originally designed the kind of symbolic expression, transformation ideas of Wolfram Language. It's kind of, combinators are pretty hard to understand and pretty complicated in their behavior. And this was an exploration that we did in sort of celebration of the 100th anniversary of the invention of combinators. In some ways, I'm glad I didn't understand more about combinators when I was first developing Wolfram Language, because there are many issues about the way that evaluation is done, which really show up in a major way in combinators, which have not bitten us in all these years in Wolfram Language, but which, as we go forward, we have to think about. And they have to do with, if there are many different possible transformation rules you can make, which one should you make? And in Wolfram Language, we have a very definite thing. We make the first one that works. And that turns out to be a thing that for practical purposes works just great. But from a theoretical point of view, you can start worrying about, well, what about all the other possible ones? What about all the complicated possible paths that you could have followed that you didn't follow? What is the meaning of all those paths? And I might have said, who cares about those paths? Until we realized in our physics project that those paths basically are what make space-time and what make quantum mechanics. So that's a reason that we have kind of a big indication that there's something interesting there, and there's something which also turns out to inform things that we want to do computationally. By the way, even after 100 years, it's still not known whether the two combinators that were defined by Moses Schoenfinkel in 1920, it's not known whether one of them on its own might be universal, and I put up a prize for determining whether that is in fact the case or not. I strongly suspect that it is the case, but that the definition of what it means to do a computation will have to be somewhat expanded to understand how computation is done in the case of this single combinator. But in any case, we've done a variety of things over this past year in this kind of world of understanding sort of the foundations of computation at the level of understanding these very simple kinds of programs and what they do. Another one that I should say that in the combinators we did, I did enough on combinators that in connection with the anniversary that I even put them all together in a book, so you can get the combinators book with all sorts of bizarre pictures of what combinators do in it, and a rather extensive history of the world of combinators and some very engaging aspects of that. In any case, so along those lines, we also looked at another thing that's from 100 years ago. Oh, nope, didn't work. Well, so let's see. Here's a better example, I suppose. These are things called tag systems, which are another type of rewriting system. More went into string rewriting, and there's sort of a question that this is back in 1921. This chap Emil Post kind of thought if he can only solve tag systems, he can solve all of mathematics. But then it turns out tag systems are really hard, and we can now understand why they're hard and why that sort of all plays into sort of foundational questions about computation. But we did an event connected with that also in this past year, and along the lines of this. No, why is it doing this? That is not how it should work. I have no idea why it's doing this. That's completely the wrong thing. Oh well. I wonder whether that's going to. Maybe somebody could help me out by. From our team could help me out by replacing this by something where this actually works, and let me know when that's done. Okay, in any case, I'm not sure I'm going to be able to show you so many of these, but another thing. Well, this is another thing we did, another event we had related to the problem of distributed consensus, which is sort of a foundations of computation meets modern blockchain meets distributed computing kind of problem. And that's another thing where we had an event and made some progress on it. I would say that in the last couple of years, the biggest news in terms of sort of basic science that I've been involved in has been our physics project, and the really quite remarkable realization that sort of from this sort of very underlying computational infrastructure, we seem to be able to actually reproduce what happens in physics. And there was a book that came out last year that was the version of the physics project book. But I'm not going to talk about this here because it will take us way too far afield, but suffice it to say that things have been going outstandingly well with our physics project. In particular, just a deepening understanding of what the actual sort of formal structure of the thing is and its connections to just a whole host of different approaches in mathematical physics. And it's been really nice to see sort of increasing absorption and excitement in the physics community across a lot of different fields in making use of what we've done in the physics project to kind of grow things in relativity, general relativity, in quantum mechanics, in quantum computing, in all sorts of different areas, causal set theory, categorical quantum mechanics, all sorts of areas that seem to now sort of plug together and have a foundation based on our project. And realizing that it really does seem that we have a good machine code understanding of how physics actually works. Well, actually, one of the things about the physics project is what I kind of assumed that, here's a kind of gallery of some of the things that came out in the first year of the physics project. But I kind of assumed that the physics project was something that would not have any applications for maybe 100 or 200 years. Maybe there would be physics experiments one could do, but there wouldn't actually be actual applications of the physics project to real things that were part of the practical world. Turns out I'm wrong. Turns out that even now we can start to see very strong, very interesting applications in a way that I did not expect. Because basically what happens is in the physics project, we've developed this kind of formalism for understanding how physics works. And it's a very foundational formalism. It's I tend to refer to it as the multi-computational formalism. And I can explain a little bit about how it works. But the thing that's important about it is it turns out it's a core foundational paradigm for thinking about modeling things. And that core foundational paradigm can be applied not just to physics, but also to lots of other areas as well. But here's the really important thing that I didn't really see coming, which is when you have a core paradigm that can be applied across a lot of areas, including something like physics. Physics has been a tremendously successful field over the past, particularly 100 years. And so if you know that the core foundational paradigm that it has is shared with some other field, you can import some of the success of physics into those other fields. So if you can formulate these other fields with the same core paradigm, you can use ideas from physics about event horizons or reference frames or whatever else and apply them to other kinds of fields. And in fact, there's something even more than that that happens, which is it turns out the very foundational theories of physics, particularly general relativity and quantum mechanics, turn out to be generic to this kind of multi-computational system. And those are essentially provide generic laws in those systems that can then be expected to be seen in other kinds of systems as well. I'll give a very brief, this is maybe a little bit too philosophical, but I can expand on it another time, but I'll give a very brief kind of outline of sort of the way I see the emergence of this paradigm. If you look at sort of the way people have modeled stuff in the world, I think there are basically four epochs, four paradigms that have emerged. Each one, even the ones from the past, are very, very useful today. The first kind of paradigm is sort of a structural one developed in antiquity. People just said, what's this stuff made of? Is it made of atoms? Is it made of vortices? Is it made of water? Is it made of whatever else? It's kind of, what is stuff made of? Is it constructed from these, spheres or whatever else? There wasn't really a notion of time directly in those models. It was more, what are things made of? How are things constructed? Then, or at most in later versions of the same thing, where is a static flow chart of how this system works? So then by the 1600s, the big innovation was this idea of mathematical modeling, the idea that you could use mathematical equations, differential equations, things like that, to make models of the world. And then one of the things one can think about is how does time enter in those kinds of equations? And the answer is basically just a parameter, a coordinate in those equations. And so when you say, I want to get the result at a particular time, you just run that time, you just say, I've got this value of the time parameter, substitute it in and get the result. That's kind of the notion of time that existed in kind of the mathematical paradigm. Then in the computational paradigm that I was much involved in kind of developing starting in the 1980s, the idea is don't use a mathematical equation to represent a system, use a program to represent how a system will work. And why is that so different from using a mathematical equation? In an equation, you're interested in solving the equation and getting this result where you can just, time is just a parameter. In a program, you expect to just say, I've got this program, now I'm going to run the program. And I'm not going to be able to know necessarily what's going to happen some number of particularly around this phenomenon of computational irreducibility, that it may be irreducibly computationally difficult to find out what will happen after some number of steps. You just basically have to run the thing for that number of steps to find out. So that's kind of the notion of time in the computational paradigm. And by the way, of course, the computational paradigm in the last 20 years or so has become very important in actually making practical models of things. It's become, I think, even the predominant way that new models are made of things in the world. But it has the feature that it has this notion of time progressing through the action of computation. But in a sense, there's a single thread of time. It's just, it progresses from one state to the next, and so on. The idea of this new paradigm, this kind of multi-computational paradigm, is that instead of progressing one state to the next, you instead have this whole network of possible states, this kind of set of possible histories, this kind of whole branching and merging collection of possible threads of time. So you don't just have a single thread of time, you have all these different threads of time. Now, one feature of that is, if you say, well, what happened in the system? The answer is, well, lots of different things happened. There are many different threads of time. The only way you can get an idea of what happened is to have some kind of notion of an observer, to actually be saying, how is the observer going to sample this kind of multi-computational, multi-threaded, multi-way kind of system? And so you necessarily have to have a notion of the observer. And that's something we are familiar with in something like thermodynamics, where we have an observer who doesn't notice the precise detailed motion of every molecule in the gas. They only notice certain aggregate properties, and that's why we end up with the second law of thermodynamics, things like that. So what we realize is in this multi-computational paradigm, when you look at kind of the low-level operations of sort of space-time, what you realize is for a certain kind of observer that's like us, who kind of coarse grains across all these different events that are going on, you inevitably get a structure that is like space-time and that involves general relativity and so on. And it turns out the properties of the observer, you can get kind of philosophical about it. I sort of finally understood something about sort of the core applications of the idea of consciousness have to do with the idea that we are computationally bounded observers of what's going on, and we have this feature that we believe time is sequential. Those two attributes alone are enough within this multi-computational paradigm to necessarily give you aggregate laws that turn out to be general relativity and quantum mechanics. Quantum mechanics is a slightly more bizarre case because, in a sense, you have this universe that's branching and merging and branching and merging. That means we, as embedded in that universe, our brains, in effect, are branching and merging just like the universe is. And so the story of quantum mechanics becomes a story of how does a branching brain perceive a branching universe? And you get all kinds of interesting issues about our extent, not just in physical space, but in branchial space, and how that relates to when we get to see quantum effects and not, and so on. But in any case, and quantum mechanics is kind of a little bit the tip-off that this multi-computational idea has to work. But then it turns out to feed back into things like general relativity. So, okay, so given that idea, one of the things is to any observer who has these characteristics of computational boundedness, sequentialization of time, you necessarily get from one of these multi-computational systems that even though at the lowest level there's all this complicated computational irreducibility going on, that there are these aggregate laws that turn out to correspond to essentially general relativity and quantum mechanics. So the thing that I sort of realized recently is that there's just a lot of other areas where this general multi-computational idea can be applied, whether it's in chemistry, thinking about different kinds of interactions between molecules. What is the chemical observer like? The chemical observer might not be the observer who just says, what's the total concentration of each chemical? It might be something that can see more of the dynamics of, for example, the causal graph of interactions between molecules and so on. That's highly relevant when you think about immunology and immune memory and things like this. They're also been playing around with models of economics that relate to this as well. And what's really interesting about these is that because we kind of know that these are sort of the same foundational formalism works in physics, and we know so much from physics, we can start applying ideas, understanding what is mathematics and the axiomatic foundations of mathematics versus mathematics as mathematicians practice it. And I'm sort of slowly understanding that axiomatic mathematics is like the molecular dynamics of mathematics, and mathematics as mathematicians practice it is more like kind of the large-scale fluid mechanics, and understanding the role of computational language as sort of a mediator of the sort of fluid mechanics level of metamathematics. But there's much more to say about that. I would say that one other area where this is important is in computation itself, and in this notion of what does it even mean to do a computation? In the case of the sort of regular computational paradigm, there's this notion of input, crunch, 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 output. In the multi-computational paradigm, there is who is sampling the computation, maybe with some particular reference frame, and that's kind of what is being seen. And so this makes one wonder, how do we generalize how that works for how we can make this generalization of the core ideas of Wolfram language into this multi-computational domain. And I think this is something we're looking at and trying to understand this notion of evaluation fronts and evaluation reference frames and so on. All right, so let's see. Well, I just to mention one a lot of the science, this has been a progression of developed technology that lets one develop science, that lets one develop technology, that lets one develop science. Thing for me in that progress was New Kind of Science, which is about the study of simple programs and what they do. it's going to be the 20th anniversary of the publication of this book next year, and sort of in recognition of that, and in recognition of all the things that people have done with these ideas, we're sort of steadily things. I mean, it's remarkable how much there is still to study in the computational universe of possible programs. And as we add in this kind of multi-computational idea, it becomes still richer. And so one of the things that kind of recently realized is this field of studying the computational universe, studying simple rules, seeing what they do, it needs a name. We're going to call it Ruliology. And we're going to have things like the Ruliological Society collecting together all those people who in the last 30, 40 years have been exploring these kinds of ideas, but haven't really had any kind of centralized platform. It's also, the other thing to understand is there's this kind of other concept of meta modeling, which is something that in a sense is what is the story of NKS, the story of the physics project, the story of multi-computation, and in some ways the story of language design, a particular thing in the world. And you say, what is the kind of, let's drill down in that model and let's understand what are the essential pieces from which that model is made. And for example, this multi-computation idea is the core foundational idea underneath that. That's another piece to this. So something we will finally hoping to launch in the next year is our Wolfram Institute. Initially, it will have this is kind of the concept is, can one have directed innovation? We've been rather successful at that with Wolfram Research for the past 35 years, and it's been very successful in our physics project. The idea of the Wolfram Institute is to push kind of directed innovation in particular areas. And the first three areas we'll be concentrating on are this Ruliology area that I mentioned. Another area is the physics project. And a third area is kind of educational outreach. Just mention a few of the things that we've been doing there. We've had our summer school for the past 19 years now. Lots of exciting projects get done there every year. We've also had our high school summer camp now for about 10 years. We've been gradually expanding our collection of educational programs. We introduced a middle school summer camp for girls this year. We started looking at a gap year research program, and we have a winter school for the physics project. There's another one coming up in a couple of months. We also have a winter school in India focused on data science. A variety of different kinds of educational programs that we're developing. We also have a whole effort in sort of opportunity programs, particularly for the summer camp, trying to get a broader range of students from sort of broader. We have good geographic distribution. We don't have good things like socioeconomic distribution of students, and we would love to figure out how to fix that. So in the category of education, we've been another thing we've been doing is live streaming. I myself have been doing a weekly. This is one good thing from the pandemic, is that I started doing these science and technology Q&As every Friday for kids and others. And if nothing else, I found them fun. And I think over the last year and a half, I have become a measurably better explainer of things as a result of that practice from doing it. But that's one thing we've been doing. We've also been live streaming. I should show, if I look at the science and technology Q&A here, you'll see lots of different episodes with 67 episodes apparently. It's nice to use our own technology here to be able to do speech recognize on the videos and generate word clouds from the videos to see what was being talked about and so on. That's a useful general capability. Now, the other big thing that we've done with live streaming is live stream design reviews. Our software development process, our software design process. The concept here is to have a sort of a completely open development process. And I know some of you have participated in these live streams, and thank you very much, because a lot of good suggestions have been made by people on these live streams. It's a great way to get input on the things that we're doing, and I hope it's useful to people to see what the actual process is, for creating the kinds of things we create, and to realize, if in case you wondered about it, it's actually kind of hard to figure out how to make things work and how to do this this process of software design. I think language design, I view language design as a very pure sort of abstract art, so to speak, that requires kind of the sort of greatest clarity I know of understanding of things to actually get right. In any case, people who follow these live streams have been know many of the things that are coming in the new version of our system. But I thought I would now go and sort of turn to talking specifically about. I've now done apparently 500 episodes of live streamed design reviews. Okay, so let's see. Okay, let's come to the usual core of these keynotes, which I'm sorry I've gone really long on talking about other things. So I'll go fairly quickly, but I want to try and cover some of the things that we have coming in version 13, and let me show you a little bit about that. All right, let's see what we've got here. Oops, not what I wanted there. Okay, well, since it's Mathematica's 1/3 century birthday, let's start with some math. So one area that we've expanded is integrals, and we've added a bunch of new sort of heuristic methods for cleanly doing various kinds of complicated integrals. There's an example lots of indefinite integrals of algebraic functions. So here we can just try, just to prove this is right, let's try differentiating this again and then simplifying it again. And I think we'll see that it actually comes back to the right thing. Okay, so another area that we've been tackling in terms of symbolic computation, one of the things about symbolic computation is how do you approximate things? You have numbers with finite precision. That's one form of approximation. You have power series. You have numbers which have plus or minus errors, different kinds of things. We have so for example, we can have a number with errors. So an around that will give you another around. It will give you something which says this number plus minus this number with some notion, some calculus of a notion of what it means to have a plus minus number. One thing that we're adding in version 13 is what we call centered interval, which is kind of a proven mechanism where it says this is this particular number, and we guarantee it's that number plus minus 7i. And so what we've done here is we're able to just compute sort of as a theorem that the result from zeta of this interval is zeta of this other interval here. So this is an important thing for kind of having provable properties of certain kinds of approximate computations. Okay, another thing in math, a little bit of a milestone in math. You know, there's this book. It's this book called Abramowitz and Stegen. It's a famous book from the 1950s about mathematical functions. And this is a book that back even from the time I was doing SMP was kind of a foundational book for knowing what mathematical functions are out there. Okay, well, I'm happy to be able to say that as of version 13, we are finally done. Every function in Abramowitz and Stegen, we now have to arbitrary precision anywhere in the complex plane with all of its symbolic properties, et cetera, et cetera, et cetera. The Coulomb wave functions were the last ones. Okay. Also in the kind of mathematical area, we've been developing a lot with PDEs. So one of the things we've been trying to do is to develop a kind of modeling language for PDEs. So here, I was going to tell this story. The main developer of this capability must have been a dozen years ago now. We were having tea somewhere, I think it was in Munich, and there was a spoon, and we were talking about PDEs. And I said, when will we be able to get a full stress analysis of the spoon? And so we've been waiting for the spoon moment ever since. And we're finally at the point where we have solid mechanics PDE components, we have solid boundary load values, we have a lot of ways to kind of represent the modeling of solid mechanics conveniently. And I don't know how long it will take to compute this. That spoon is, it's a difficult spoon, I guess. Come on, wake up, do your thing. Okay, there we go. So this generates a bunch of results. Now we can try and make a plot that shows the result of displacing, of putting this this force, this load on the spoon. This is part of our plan of having different kinds of modeling languages, symbolic modeling languages to represent physical kinds of things. And this is adding things related to PDEs around that. So, okay, there's our spoon with its deformation. Okay, let's turn to another area. Let's talk about another real world thing, geo computation. So here, let's get, so one thing that is coming in this version is vector maps. So we've had maps for a long time, but we've always had maps where we have tiles of the Earth that are quite high resolution, but they're at fixed resolution. One thing that's coming in version 13 is the ability to have vector tiles, a fully vector representation at arbitrary resolution that allows you to get very sharp maps. The thing that we're doing by default initially is to provide vector labels and bitmapped background, although you can also get a vector background as well. Now, there are many, many advantages to being able to do everything in a computable way. So, for example, if you want to label the Earth, we can now get nice labels even on projections that are quite wild. That hasn't been possible before. If we just had the labels burnt into the tiles, we couldn't do that. And we can take, there are different stylings for these things. This is one that has a fully vector, everything is vector, including the background. So you can see that background is high resolution, is arbitrary resolution. You can, and then we can also, because everything is computably represented, we can restyle everything. We can restyle all the different kinds of elements that exist in maps so that we can produce very beautiful maps with these. We've been steadily progressing with sort of getting all the details of time right. You might have thought that, so just like there are datums for geography where you have to map from a lat-long coordinate to say what actual position on the Earth does that lat-long correspond. There's a similar kind of thing. UTC, the most common kind of time, is not, that is a representation of time that is sort of approximates the rotation of the Earth, so that you know so the sun rises sort of at the right time every. UTC depends on the rotation speed of the Earth. And so, for example, we could just look at what is the difference between UTC and atomic time based on sort of absolute measurement of time. And these are the leap seconds that have been added over the past, since atomic time and UTC started diverging. And in principle, the Earth could speed up. The Earth is generally slowing down over time, but it could temporarily at least speed up a bit. And then we'd subtract leap seconds. But for now, we're adding leap seconds. This all seems very detailed, but as we're moving towards being able to do all sorts of astronomical coordinate systems and precision computations in astronomy, it's necessary to get these time things right. And in astronomy, we'll have all kinds of relativistic features of coordinate systems, all sorts of interesting things like that. Let's see. We have also got, that doesn't look right. Okay, another thing that's come is geograph value plot, where we are able to take elements in geography and show like the flow of things between different places and show them using a geograph value plot. Well, let's see, I think I already showed actually a vector displacement plot, and that doesn't seem to have gone correctly either. That's okay. All right, let's see. In terms of visualization and plotting, here's another thing that's come. This is, usually you plot a curve from between a minimum value and a maximum value. What if the curve goes off to infinity? well, what if you want to look at it over an infinite range? We now have a sort of default way to remap everything to a finite range. So this is showing these functions going off to plus minus infinity, being mapped into a finite range here. Another thing that's coming is multi-element plots. So this is showing 4 plots with a layout of in 2 columns. And what's important about this, and there's a lot of tricky cases here, is dealing with the fact that the axes are just shown on the edges and so on, and you can really gang together lots of different sort of subplots there. So that's putting together different plots. Another long requested thing has been the ability to have different axes. So this is now available in a very general way. This is a multi-axis plot, this with different scales on the 2 sides, and you can deal with having many more curves, and it'll do all kinds of elaborate things with multiple axes and so on. Okay, so that's another thing in visualization. Another area we've been developing is spatial statistics, where you have data that is represented by points on the Earth. So we could say, let's just take a bunch of samples of something at different places on the Earth, and here's samples of those values in different places. Now we can do the equivalent of finding a fit to those things, but it's a spatial fit. So now we're finding a spatial estimator here from that data. And now we can go and let's say we can pick some 2,000 random points. And now we can go and make a plot of the values of that space between those values to sort of fill in the data in this from this. Okay, next area. Let's talk about image processing. Okay, let's see what we get here. So let's take. So here's a bunch of images, and this is a new function, image stitch, whose goal is to figure out key points in all these images and try and line them up, and eventually use machine learning kinds of things to sort of blend images together. But there we go. This takes all those images and stitches them together. Coming soon, I suspect, will be a spherical image function relevant for things like VR and so on, that will be able to be stitched from individual images. Okay, so another thing we have in version 13 is more in PDF import. This is something that came in the previous version, the ability to really take a PDF and import it first as images. There are 5 pages of PDF images at some resolution. Then we can also now, or for example, we could just say import that as plain text, and then we just get the text. Or we could say now, new capability, import that as page graphics. And so then each one of these things is an actual piece of graphics that you can do computations with, and you can sort of untangle in different ways. Okay, so this is full resolution graphics. Okay, so that's a bit on image processing. Okay, big thing that first came in version 12.1 was the introduction of video. What we've got in version 13 now is one important thing is that video is now viewable directly in a notebook. So there's a video viewer built into the notebook system. And there's our video playing in a notebook. And now we can just say we've got this video, and we can just start doing functions on this video. So we can say image dimensions. So the image processing functions mostly work now on videos as well. So we could say something like image crop. So there's the original video, and now let's crop that video. So now it'll go through and process these video frames. And the result of that piece of, quotes, image processing will be a new video cropped as we specified there. Okay, so now that's an operation we can do on a video. So now another kind of thing we can do, other things is, for example, we could take that original video and we could make an overlay video. We could either have a video or a static image that we overlay onto another video. And so here we should get a version of that video that has this kind of a spiky mark on it. And then we'll see the same video, but now with that overlay on it. Now we can also take, let's see, we've also got, let's say here, for example, let's make a bunch of videos. We're going to apply a bunch of image effects now to videos. Okay, so this is different kinds of image effects here. Videos are big, so it can take a while to compute things in them. Okay, here we go. It's doing all of these. Okay, so this should now make a list of videos. And, it's kind of weird because we can actually play those videos directly in the notebook inside the list. Okay, weird stuff. So now we could take that result and we could say, make a grid video out of all of those. So now it will take that list of videos and it will make a video which combines all those videos. And so now we've got this video that is a grid of videos there, a grid video of videos. Okay, so now let's try some other video operations. So here's just a sample video, and then let's go ahead and say, just give us the list of 10 frames from that video. There's a little animated video. Now we can also make a snippets video where we create a video that is kind of a trailer for that video by just sampling the video in different places. And so this now will be a small video that has two different pieces of this of that original video that have been sampled as snippets. Okay, let's look at another thing here. So let's say we have an image. Here's a hopefully, come on, wake up, image. This isn't an image. I'll generate an image. Okay, here's an image. That's probably a rather high resolution image. Okay, so now I want to make a tour video. So this tour video is going to kind of, oh my gosh. Well, I said it was a high resolution image. It's a 1 minute process to do this. What this is going to do is it's going to make a video which interpolates between looking at one part of this image and it's going to walk around this image, showing us different regions of the image. Let's just, oh dear. This is a way to all right, come on, I got to show you this. Since I just loaded in this image, I could do it on another image as well, but the kind of the idea here is sort of everything integrates together, whether it's images, video, being able to create videos programmatically. You could create this path programmatically by specifying some function that represents how you move around this image and so on. And hopefully we will be generated with our frames in just a few seconds here. And then we can see whether this actually did anything useful. All right, come on, let's hope it doesn't have another step that it has to follow here. There we go. Okay, so now here's our video. And now let's see what it did. So that should, okay, it's just moving now in discrete I see it's loading in that video. It's a rather high resolution video. So it's just moving around, interpolating between those points that we told it to go to. Well, let's do one more example of this. Okay, so here's a famous image. I'm kind of reminded of our physics project here because this was an image from the early days of quantum mechanics. We could go ahead and find faces in that image. Let's go ahead and find the faces in that image. And then we could make a shortest tour between those faces. We could sort those faces in a sort of shortest tour way. And then we could go ahead and try and make a tour video in which we go and visit different people in that video. Okay, so there's old Albert, and we move around here, and many of those people are at least recognizable to me. Not that I think I met any of them, unfortunately. But that's so again, this is a programmatically generated tour video, and we can see many things coming along those lines. Okay, next topic area is machine learning. So one of the things we're doing in machine learning is to add videos as a type of thing that can be processed by machine learning. So this, I think, is a network that tries to find what human activities are going on in a video. So we just fed it that little animated short, and it's got all kinds of weird human activities, like playing laser tag with 0.505% probability and things. 0.5% probability. So that's something, is the integration of video into machine learning. Another thing is new algorithms for things like feature space plotting. So this is now a new way of doing large-scale feature space plotting. Hopefully this will go fairly quickly. That's one kind of thing. Another thing that I would say that one of the big pictures of our efforts in machine learning are to provide capabilities at two levels. First, at kind of the low level of individual neural net components, and second of all, at the level of kind of super functions. And two of our very successful super functions have been predict and classify. We just give a bunch of examples and say, generate a classifier, generate a predictor from these things. And that's a very good way to do machine learning in a very automated way. We're using machine learning to automate machine learning. We have a new type of super function that we're introducing in version 13. I don't know why this is taking so long. I guess it's a guy has 50,000 points to render and things. All right, maybe we should quit on that. Let me see whether I can put in another. Let's give up on that one for now. Don't have time for that. I just was generating something. Oh dear. Oh well. Anyway, so the new type of super function is what we call content detectors. So instead of saying, what is this picture all about? It says, for example, in this picture or in this piece of text, extract things that are like this as subpieces, pieces of content from within the whole object. So here we trained a content detector for text on those phrases, telling them what the pieces that we cared about in those phrases. So now we can feed that, we can apply that content detector to those strings, and it will pick out. Of course, what it's doing here with text is it's using everything it knows already about text, and then it's just adding on that content detector mechanism on top of that. And for text, this can be done quite quickly. Here's an example for images, train an image content detector. This, I'm afraid, is not so quick. That's a much harder problem. And so this is like a 20-minute process to train that detector, and something went wrong there. But anyway, it's got 20 minutes to run, which we're not going to wait right now. But the whole point is that you can custom train an image identifier now to find not just what the whole image is of, but find every banana in this picture, for example. And you can train it with comparatively small amounts of training data because of the fact that it's leveraging everything it already knows about images and how to recognize things in images. It's able to do surprisingly well with rather little training data, although the actual training process can take a while of computer time. Okay, let's see. Another thing we have, this is a book about machine learning written by person in our machine learning group that should be coming out soon. I think it's going to be a nice book that really introduces machine learning in the context of what's possible in Wolfram language and so on. All right, that was it on machine learning for now. Let me talk about another area. Let's talk about trees. Something that we introduced in version 12.1 was the idea of trees as fundamental objects in our system. And the trees at some level are like graphs, but they're not really like graphs. There's more to a tree. A tree has has a whole ordering structure to it that isn't quite like a graph. Okay, so we're adding in version 13, there are some new capabilities for trees, like tree layout functions. You can do all sorts of different kinds of layouts for trees and so on. You can also you can make this is making a graph from a tree from a graph. In this particular case, we can now here's a thing which actually relates to some of the theoretical things I was talking about. Let's say we do a tree scan. We say we scan this tree, then we're going to visit these nodes in a particular order. So the default is to do a depth first scan of the tree. So we go 5, 6, 7, then 2, et cetera, et cetera, et cetera. But one of the things, and it's related to evaluation fronts and multi-computation and all these kinds of things, is the notion of parameterizing the tree traversal order. So a famous one is breadth first order. but we have all sorts of different parameterizations. You can think about these if you like to think about things in terms of relativity, of general relativity, or relativity in general. These are essentially reference frames that you're using to observe this tree. And you can think about these different evaluation fronts as being like different ways to parse the structure of this tree. In the same kind, or different equivalence classes of layers in the tree, so to speak. So that's another thing that's coming there. All right, so different sources for trees. Here's an unusual source for graphs. This is an inbox, a mailbox, and this is showing the threading structure of a mailbox by looking at the actual structure of the messages in the inbox and seeing how they are threaded together. So that's okay. So another thing we can do here, let's move on to graph theory here. Let's just make a random graph, something which is also a little bit reminiscent of some of the things we've done in the physics project, is find isomorphic subgraphs. So this is now going to find all the 4 cycles in that graph. Surprised it takes quite so long to find them. Oh, there we go. So notice that each of these has actual definite labeled places. Those represent the 4 cycles that exist within this random graph, sort of reminiscent of the hypergraph transformation rules that we use in the physics project. The universe is really good at graph isomorphism implicitly. So, okay, next in graph theory is graph coloring. So here we can say find vertex coloring. So there's a map of Africa showing the neighborhood relationships between countries. And why isn't that a graph object? That is a graph object. Weird. Absolutely weird. I don't know why it doesn't think that's a graph. Well, I would have thought that was a graph. We can regenerate the graph. Anyway, what we should have seen is, and notice that I'm running the very latest version of version 13. We just froze the code for our preliminary version just yesterday. So this is a very, very fresh version of things. But had we seen this do the right thing, it would have told us that there were 4 colors we needed to use to color this graph appropriately. And graph coloring is useful for many, many different applications, whether it's register allocation for compilers or all sorts of other kinds of things. Okay, moving quickly through geometry. This is a new capability in geometry. Geometry, again, it's like approximating numbers. There are different ways to approximate geometry. We can have our region specifications, which are perfect and symbolic and represent regions in terms of let's say, mathematical functions and so on, saying this is, a sphere within this bounded by this algebraic formula. Or we can use something like a mesh region, where we're saying a region is put together by just having these different mesh pieces. Another thing we can do is to use constructive solid geometry, in which we take certain primitive regions and we do certain operations on them. So this is something doing a region intersection there, where we can now compute with these approximate geometries, so to speak, in a different way. So there's a whole sort of world of those kinds of geometries. Okay, so a major area of Wolfram language that's been rolling out since 2019 is chemistry. And so here, let's see if we can make this work. So chemistry, this is going to, we're now doing computations with molecules. And something which is coming out of things from the physics project is, can we actually take what we know about molecules and what we know from the physics project and this whole multi-computation idea to actually understand how to do computation, not about molecules, but with molecules? And that's sort of a coming attraction. But for here, those are just symbolically represented molecules. I can say, though, the isomers of this particular thing, and these are 3D renderings of those isomers. And that's something that's happening here now. Now, another thing we're starting to do is to work on chemical reactions. We're just beginning on chemical reactions. We can say, balance that chemical reaction, we get that result. We can say something like, get a little bit of computable information out of that. Chemical reactions are a story of graph rewriting. And they're a story that looks incredibly similar to some of the things that happen in the physics project. And this whole idea of multi-computation and all the possible things that can happen to chemicals and so on, it's all a deeply related set of ideas. It's also related to automated theorem proving, because all these different, when you do a chemical synthesis, you're trying to find this path through all these different chemical reactions that gets you to the product you want. And so they're a collection of very related ideas which are wonderfully converging here. Okay, another thing we added is biosequences. So let's take a typical biosequence here. It's base pair sequence, and we can then we can turn that into a molecule and actually visualize the corresponding molecule corresponding to that that base pair sequence. There it is. And now we can, another thing that is new here is we can make a molecule graph. So that's really being very explicit about the graph theoretic character of organic chemistry, so to speak. We can also, new in version 13, we can also do, put in various kinds of secondary structure and hybrid strands and things like that. That's a base pair sequence that has had an extra bond connecting some of the pairs there. Let's see what this one is. This is maybe a slightly more complicated one of the same kind of idea of a thing with a secondary structure there. All right, let's move to a completely different area. This is another piece of sort of the real world that we've had in Wolfram Alpha for a while, and we finally got to the point where we can incorporate it in Wolfram Language. This is flight data. This is the flights in the last 24 hours that went from Boston to LAX. And we can now say, let's get for all those flights, let's pick up their flight paths. And you talk about GD6, we talk about GD6 a lot. Let's see some actual GD6. I'm trying to figure out whether the wind is sort of analogous to the force of gravity. Oh, come on. What happened here? Eek. Something went horribly wrong. Well, that should have shown some beautiful GD6. Don't know why that didn't work. It's also very suspicious that there's something there that says coordinates weren't found. Who knows? We're a little bit at the mercy of the feeds that give us flight data, but it should be the case. I mean, if we take one of these flights, let's just take one of those flights. Let's see whether we can get a flight path from that. And let's see. That's very odd. Let's see. Let's just look at the properties of this. Actually, we can just say, just for fun, let's say the data set of properties here, and that should give us a bunch of information about that flight. Okay, there's the time series of its altitude and things like this, and there should also be the flight path there. I don't know why that didn't work. Let's say, well, okay, so that will show us the flight path, or this will show us what is happening here. That will show us here, let's just have one thing to plot. Let's do dateless plot of the altitude as a function of time. I guess that flight is still flying right now. Okay, so that was that. We can also look at, let's try this. Okay, more data about other kinds of things. It is fun to see those GD6, by the way, I recommend it. More data, we've been continuing to work on lots of different areas. There's nutrition label for a chocolate chip cookie. We've done more on food data. We've done more on weightlifting exercises, all kinds of physics things. Here's, for example, physical quantities. This is the beginning of a large build out of being able to do computable operations, not just on the values of quantities, but on the notion of a quantity. So that's another thing. Okay, completely different area, cloud expression. So we introduced a number of versions ago this idea of a cloud expression. A cloud expression is a persistent storage of an expression. It's something where you could have a big cloud expression with hundreds of thousands of elements in it, but it just sits in the cloud, and you don't have to load it into your current session. You can just extract a piece of it. So let's just rewrite this cloud expression, and you can do operations on it. So let's say you say that, and then we could say, for example, get the cloud expression, and it won't look very exciting because it just will get that expression with that piece replaced there. But what's important is this lives in the cloud. This expression is being efficiently manipulated piece by piece in the cloud in what is effectively a local database in the cloud. So it is a persistent thing that is locally manipulable in the cloud. And you can also do things with proper full databases, but there's all kinds of setup and administration required with sort of a full database. This is a kind of a cheap database that is effectively stored as alongside your cloud objects in your cloud account. But it's something that is persistent and lets you progressively compute with it, just like an expression. Okay, so lots of things to do with the cloud, smoothing out lots of interactions with the cloud, things about running system modeler now in the cloud. That's so you can take systems engineering models and run them in the cloud and so on. Okay, another thing I'll mention, I mentioned the Paclet repository. One thing that is necessary for the Paclet repository, we don't want a land rush for people trying to find small Paclet names. And so one thing that helps that not happen is by having a context aliasing mechanism. So what this is doing, it says, I need the developer context, but I'm going to call that context dev. So now I can use dev backtick as an alias for for that context. So your context name could be a big long name, but now you can use that context and alias it to something short. Okay, so let's talk about another big area. Another big area is user assistance and code assistance. So a big feature of our system is things like syntax coloring, auto-suggestion, auto-completion, these kinds of things. Something that is a long time story is, how do you make sure that the brackets you type are matched? Okay, so normally if I type F and I type an open bracket, I'll just get the open bracket. But now you don't just get the open bracket, you get a closed bracket as well. And if I keep going and I type G, I'll get an open bracket, H and an open bracket. And so what I've got here is something which is auto-matched brackets. Now, as a practical matter, when I'm typing F bracket X, for example, well, let's say F of G brackets Y, and now I want to type another thing here. What do? Well, I can just type through that bracket. So I just copy that bracket, I just type another bracket, and then I can keep typing. And this is, once you get used to this, this is really useful because the total number of brackets you have to type is dramatically reduced. You can also use an arrow key. You'll soon also be able to use a control period to get out of the local of the thing that you were inside of in those brackets. And it's pretty good at figuring out when it can, in fact, add an auto-completed bracket, auto-matched bracket. So, okay, another thing that's come in this version is auto-operator renderings. So if I type a single bracket, I get that. If I type a double bracket, I get that thing, which you might be able to see there, is a nice little typeset double bracket. So I can now type, now if I type in between those double brackets, I'll get this. The same thing's going to happen with all the usual kinds of operators, you know, like, for example, you can make a function with a vertical bar dash greater than x squared, that makes a function. But these things are now, they are things that are sort of coding ligatures. They're things where you create this character sort of immediately, but it is stored as the character's broken apart. It just is created on the fly. So if I backspace through it, you'll see it break up. Okay, there's some things to do with iconization that have been added. I could, if I select just a little piece of this and I don't quite get the parens correct, I can say iconize that, and I will be able to iconize it even though I didn't have exactly a complete sub-expression. That will still be iconized there, and if I evaluate that, I'll still see that it evaluates correctly. We've been working a lot on code analysis. Let's see. We are also working code analysis where we're trying to heuristically say the thing you typed in, it's like a grammar checker for English text. The thing you typed in, well, it is a bunch of words, but, and it might even be syntactic, word-wise and spelling-wise, it might be correct, but it's not likely to be meaningful. And we kind of give you an indication of that. And we've been working towards using a variety of rules and machine learning and so on to be able to do efficient code assistance. You'll see more of that coming in subsequent versions. Okay, so let me just show you a few more things here. This is, okay, I have to go up here. This is the code formatting. We've kind of enhanced the way that that works. Come on. Wake up. This is the code formatting palette. And if I go and I say, I don't know why I'm even showing that one. Oh, I see. Well, let me show a different thing. Okay, so here's a cell. And now I say, how do I want to format that cell? How airy do I want that cell to be? Let me make it area. And now what will happen is, I hope this is working. There we go. So that's a super airy rendition, ridiculously airy, actually. And we can go down and make it less. Why is this running so slowly? We can make it less airy. We should be able to make it, well, this is broken. We should be able to make it less airy. As we move this around, we'll see it change its airiness, and we can select the airiness we want. That's based on a whole collection of custom line breaking rules that you can separately adjust if you want to, and then you can kind of store your preset preferences for line breaking there. Okay, we're almost at the end here. I wanted to show you form notebooks, and let me just show you, I think form notebooks are a way of creating a notebook that you can use as a form that you can fill out, where you can then extract pieces from the form. So this is a form authoring notebook, and we could say enter something here, and then we could say, insert here a form element, insert, for example, a slider there. Okay, it's asking me for various things here. I could preview that, and that will be a slider. And now what I could do is I could say generate this, and I can generate a document that will be a form that is a form notebook. And when I submit it, I will get out of it an association that represents what I have entered in this notebook. And the point is I can generate, it's not just like a form which has input fields and things like that in it. I can have a whole rich piece of notebook. So I could write an essay in here, or I could have a piece of documentation that is automatically getting processed, or I could have a definition notebook for a new kind of repository or something, which is all presented as a form notebook, which when you submit the form notebook, its content goes into an association which can then be processed computationally. Okay, so that's the idea of form notebooks. Now there is an additional piece to this, which is what we're calling a question notebook. And if I say create notebook of question notebook, this should create a question authoring notebook. And so this is like you want to make a quiz or something like that. This is something that allows you to do that. And what you'll find here is a whole variety of different kinds of, a whole variety of different types of questions. So for example, you could have a multiple choice question here. You could have a question that involves putting sliders on a, putting pins on a map, all kinds of different things. From this question authoring notebook, you can then generate a notebook that contains the quiz effectively. And now when you submit the quiz, you can. That's right, isn't it? Well, maybe it put a different answer in there. But anyway, it will either give you instant feedback, or you can tell it to give to send the results to a central place where they can be graded or whatever else is happening or processed in some way. But so this is now a workflow to use notebooks and use all the capabilities of notebooks, including and do all everything using Wolfram Language to create these kinds of sort of question framework things. And there are very sophisticated things like code equivalence, which you can do when you're given an answer. It's like, is this code equivalent to this other piece of correct code, so to speak? Those are things that you can expect to use in a question notebook. So that's another coming attraction for 13. Okay, one more thing I'll show you here. Another area is the ability to represent a web page symbolically within the language. So web pages have all kinds of special features. They have CSS that defines all sorts of elaborate things. And this is, let's see if we can just pull this up. So this thing here, when I cloud deploy this thing, unfortunately it won't work in the version I have right here, but if I were to cloud deploy this thing, I would get a web page here. Now let's look at what this web page is doing. It's got web items, it's got web columns, it's got a thing called interface switch. That's a responsive, that's a thing that is saying, if it's small, do this. If it's got, it could say if it's a mobile on a mobile device, do this, and so on. That symbolically specifies a web page that now will know that it should switch to having these margins if it goes wider and so on. Okay, so let's look at another example of that. So this is now a more elaborate web page that actually makes calls to Wolfram Alpha and computes things with cellular automata and does all kinds of stuff like that. And now let's get the corresponding page for that. And now, where is it? Did I get the wrong page? Yeah. Oh no, that might be the wrong page. Let's see. Maybe this is the right page. Let's try this one. Oh, there we go. So that's what that piece of symbolic code generated, this website, which now has sort of some responsiveness. It has these buttons up here, which you can press that will compute things in Wolfram Alpha, or you could send these things to APIs. You can just mix full Wolfram language capabilities with full web capabilities. So it's a way of getting the best of both of those kinds of areas. And you can have fun by having very programmatic. This is a nested web element. And now if we look at that, if we we'll get this thing here, that was specified with random colors being picked on the CSS side. Effectively, what's happening is that these specifications are being compiled into HTML plus CSS. As our compiler develops further, we will be able to compile more things into pure CSS, WebAssembly, those kinds of things to deploy as pure websites. And, for example, we can expect that is spectacularly not what I wanted. I was going to show you a beautiful web page that was deployed using these kinds of technologies, but I can't because it was set up incorrectly. All right, so that was a very quick tour through version 13. I would say that one of the things that's been sort of a lesson of the last few years is the build out of some of these big sort of application areas like chemistry. Another sort of big build out has been in physics and quantum computing. And so, for example, this is something you can find right now in, there's a Paclet that, why is this taking so long? There's a Paclet that you can load in now, which is our quantum framework. And it is very cool that that quantum framework compiles into multi-way systems underneath for some purposes. So it's basically making use of our physics project. But here we've got something which is sort of a representation of a quantum circuit in something that looks a little bit like a neural net type thing where a series of quantum operators are being used. Okay, so we could take that thing and we could show a diagram of that quantum circuit, just like we can show diagrams of neural nets. And we could then say, let's make a quantum state here. Okay, let's find the amplitudes in that quantum state. So there's a representation of the amplitudes in that quantum state. Let's have a fancier quantum state here. And let's now apply that quantum operator, quantum circuit operator, to that quantum state. And now it'll crunch for a little while and give us a result of a measurement. We could say make a probability plot of that, and we'll get the result. If there was an actual quantum computer, if that really makes sense and is possible, which our physics project makes one realize that it's a little bit more complicated than one might have thought. But the formalism at this level is still perfectly intact. The measurement, how measurement works, is a bit of a complicated story. Not so obvious how that will work in real cases. But this allows one to get presumably the same results from an actual quantum computer, although not quite as fast, one would assume. Okay. Well, it's a general feature. You know, this is a Paclet that will be on our public Paclet repository. In general, we are sort of previewing lots of things in things like the function repository now, sometimes way ahead of when they will be able to be integrated into the language. This is just a feature that we've had in Wolfram Alpha for a long time that is now getting integrated into the language. And I'm not sure whether that is going to work, maybe not. Something isn't working about that yet. Okay, here's an example. That is very weird. Is this going to work or not? Yes, it is. Okay, this, I don't know why it showed that in version 13. This is just an example of something coming through the function repository. This is fractional differentiation. This is the nth derivative for arbitrary non-integer n of sine x, or we can say what's the square root of the square root integral of 1 over x. So we get that if we were to apply that square root integral again, we would presumably get, let's see, we would get, oh, we got to do some full simplify on that. We would presumably get the actual integral. Okay, it's a little bit more elaborate because it's got conditions associated with it, but that should be the actual integral after it's been sort of square root integrated. So why isn't this immediately built into the system? The reason is that to build in something like fractional differentiation into the system, we would want it to really be sort of globally applicable, and there are different methods and definitions for fractional differentiation. We will want to cover all of those, but we're trying to cover a particular instance of fractional differentiation for a particular class of functions and so on, and for it, specifically for symbolic expressions and so on, we're trying to cover that now rather than 10 years from now. And so we're putting this in the function repository to sort of as a preview of functionality. All right, well, there are many things that are coming. This is, I've shown you some things that are coming in version 13. There's a very energetic development pipeline extending many years past version 13. Lots of things that are coming. I mentioned a few of them. There's a big game theory system that's coming, a lot of code assistance stuff, a notebook toolbar, lots of kinds of privatization of system services, lots of things to do with different kinds of array manipulation, a kind of new calculus of arrays. Did I mention multi-computation? That's a big thing which I hope will stimulate a lot of things which can be where meta modeling can be used to deliver lots of new kinds of models for things that can now be used in our computational language. And finally, there's also the compiler. I think the compiler will be a transformative feature of our system, and we now have a very energetic effort. The compiler is very difficult. It's steeped in abstract type theory, meets a lot of practicality, meets a very large existing system. But when it is, as the compiler gets rolled out, we have been using it internally, and many of the new features in version 13 were created using the compiler, and it's both efficient and very robust. The code that is generated by it directly into machine code with many possible targets, not just CPUs and so on. And the challenge is to provide kind of the infrastructure to make the compiler readily accessible and efficient on lots of kinds of things. And that's something that I think you can expect to see coming in the not too distant future, and something that I think will be quite transformative as far as the ability to do to sort of have absolutely no compromises. Whatever kind of code you write, whether it's procedural code for that 1955 computer, you'll still be able to run it. By the way, another thing we have coming, actually, previewing version 13, is a virtual machine function. And the virtual machine function allows you to emulate other kinds of machines. We might even have an IBM 650 being emulated there. I know we have a PDP-1, for example, that you're able to emulate in the virtual machine emulator, along with register machines and Turing machines. And in the future, a lot and things like Ethereum virtual machines from blockchains, and in the future probably much crunchier, full serious big machines, so to speak. That's just another sort of factoring of this kind of it's a recursive mechanism for thinking about this computational process. But anyway, so well, that was a sort of very quick tour. Not so quick, actually, a 2.5-hour tour of some of the things we're doing. There's just an awful lot of stuff going on. We're steadily progressing, trying to build artifacts from the future, but build them today. And I hope people will find the things that we're building useful, and we appreciate feedback. Please do make sure to help us communicate. We think we built this wonderful tower. Help us to actually communicate what we've built. Help us to actually explain this to the world and use it yourselves. You know about this thing. It's kind of a too secret weapon at this point. I think that it is an important goal for us to be able to actually deliver not only the capabilities that we have, but also widespread knowledge of those capabilities now rather than many decades from now. I mean, I think it is striking to me, if I look at the last third of a century, at the ideas that we had in version 1, which are still far, far from being globally absorbed, far, far away. You know, the idea of notebooks finally made it 25 years later, which I thought was one of the conceptually simplest things that we did. The other things are still a long way away. And I think, judging by sort of the progression of time, as we can see, eventually it is an inexorable thing that these kinds of ideas and sort of the kinds of things we have in this computational language, we can see the pieces of it being used, including by many of you now today. But for most of the world, these are still artifacts in the distant future. And it's something that I consider an important mission, and I hope you'll join us in this mission of kind of communicating these artifacts from the future to the world today. But I think that's all I had to say here, and I hope you'll enjoy this conference, and I hope you'll be able to hear about a lot of the things I've talked about here in much more detail in other sessions at this conference, and I'll also be doing a Q&A on Thursday, where I'm happy to try and answer further questions. And I think there is also our networking space is still up and running, and I'm going to go there in a moment, and perhaps I'll see some of you there. So thank you very much, and enjoy the conference. So bye.